Welcome to the Missing Pages, where we explore science and history that you might not find in your average textbook. My name is Lee, and my co-host Kausar and I are both scientists. This means we spend a lot of time being curious about things, and the history of science is no exception.
Our understanding of science is built on thousands of years of knowledge from all across the globe and all kinds of people. Yet, we're often taught that a majority of the scientific knowledge comes from a very limited part of the world. That's why we'll be highlighting the science and history from outside of Europe that has been foundational in our understanding of the world today, but is often left out of the story.
Whether you're a curious mind or a fellow scientist, join us as we uncover the missing pages.
Our episode today focuses on what mathematics looked like historically in Asia. For a lot of us, when we think about mathematics, we imagine the days we spent in classrooms learning about algebra and the Pythagorean Theorem and the quadratic formula. But what's interesting is the amount of history behind this knowledge and the tons of people that worked to make it happen. For those of us who don't pursue careers in mathematics, we wonder, when will I use the hypotenuse? Or what purpose will the quadratic formula serve me? But mathematics is and always has been integral to society. We will talk about what mathematics looked like historically, its sources and its origins, and how it relates to what we know now on today's episode of The Missing Pages.
So there are lots of different problems in history and everyday life that would have required mathematics. Most mathematics in the ancient world circulated as kind of geometrical riddles amongst people whose trade required mathematics. For example, carpenters, priests who had to construct altars, people who had to collect taxes, or just general bits of practice amongst communities of tradesmen. And when they're written down, we find them oftentimes in things like rough calculations on papyrus in ancient Egypt, for example.
Both the words algebra and algorithm have their roots in Arabic, and they date back to a period of time after the life of the Prophet Muhammad, and a couple of centuries we think of now as the Islamic Golden Age. So their survival into English in the present day is because of the contributions made by scholars in the Middle East during that time. Particularly, we remember Al-Khwarizmi as being the inventor of algebra. So Al-Khwarizmi worked for the caliphs who were the rulers of that time and became like an astronomer, royal basically, and head of the library called the House of Wisdom in Baghdad. So these were all great kind of contributions to scholarship at large at that time.
This book is considered as the first work to determine how to apply operations of algebra to calculate an unknown quantity. One of the key concepts in the book is al-jabr, meaning restoration, which refers to adding a number to both sides of an equation to cancel terms out. This is where the term algebra comes from. The second book was based on the decimal position number system developed in India a few hundred years earlier. In the 12th century, these texts from the Middle East and the rest of Asia began to make their way into Europe through translations, changing the way mathematics was done in the West. The word algorithm comes from the Latinized form of Al-Khwarizmi's name, algorithmi, and Al-Khwarizmi.
In historical terms, it's easy to underestimate how much mathematics relied on memorization. If we go back to ancient or even medieval times, people had to remember those numbers, right? So, for example, in the Sanskrit mathematical tradition, tables of signs were remembered by a code called Katapayadi that mapped the alphabets of Devanagari onto numbers in such a way that people could compose verses that were actually encoded tables of signs. Now, these verses had a rhyme scheme, which meant that if a number was incorrect, it wouldn't. The prosody, the maths of the poetry, if you like, would be incorrect, and the practitioner could correct. So, a lot of these kinds of elements of, I guess you could call it the art of mathematics, are what we find when we look at the historical record. So there is difference there.
In talking about the sources and origins of mathematics, a key part of history includes the House of Wisdom, also known as the House of Baghdad or the Grand Library of Baghdad.
The House of Baghdad is basically a research center set up by the Abbasid Caliphate in about the 8th century AD. So it's a bunch of scholars of, mathematics, astronomy, Quranic law. There's a bunch of accountants in there because effectively what they are is something called a divan, a tax office. The House of Baghdad starts publishing all kinds of documents on metallurgy because they need to control the coin supply, which means that they need, the mathematics of fractions, which means they need mathematicians. What starts off as a really boring state administrative project eventually comes to encompass all fields of knowledge then know. So this is kind of like a major, I'd say, turning point in the history of mathematics. And it's kind of the intellectual atmosphere that algebra comes from.
The current numerals that we use today, from 0 to 9, developed from, integrating several different number systems from ancient India. But they appear in an Indian document known as the Pjamescowie manuscript. Dating of the manuscript is a little bit hazy. It could either be as early as the 3rd century or the 9th century of the Common Era. And if you look at the numerals written in that manuscript, it's fairly easy to see the correlation between the way we type them out on a computer today. And it's also a fully developed sort of place value system with the use of decimals and 0. These are all kind of conventions of the number system we take for granted today, but certainly weren't common to all ancient civilizations. The Hindu-Arabic numerals had several advantages over the Roman numerals. Roman numerals are not strictly place value, so you have numerals for things like 5, 10, 50, 100, and then when you want to have 3 50s, or you have to put the numeral 3 times. So instead of having a numeral where their place in the order is how the value is determined, the value is determined by the actual numeral itself. So that's a little bit of the difference between the systems. But the critical thing is that place value number systems really facilitate calculation much easier than systems that are not place value.
A prime example of the Eurocentric focus in our education here in North America is the Pythagorean Theorem. It's a theorem we're all familiar with, and whether we know it or not, likely apply it to our daily lives when we choose to go the shortest distance, the hypotenuse, instead of all around, a plus b. But what we didn't learn is that the theorem that we attribute to solely Pythagoras was also discovered in other parts of the world, like China, where it's referred to as the Gougu Theorem.
The Gougu Theorem, or as we know it more commonly, the Pythagorean Theorem, is that a squared plus b squared equals c squared. So it's a theorem about right-angled triangles. And it says that the sum of the area of the squares on the two sides subtending the right angle in a right-angled triangle is equal to the area of the square on the hypotenuse. The name of the theorem today comes from the ancient Greek mathematician Pythagoras, who's credited for knowing the theorem and possibly proving it, but it was proved in this ancient Greek text called the Elements, Euclid's Elements, which was a classic text used throughout training in mathematics in Europe up until probably the 19th century. It was a very prominent text. So the name, the Pythagorean Theorem, is given to it from that sort of Greek European tradition. But what's interesting is that the theorem was also discovered independently in what we know as the Warring States period of ancient China. It appears in one of the oldest manuscripts from that time called the Zubi Xuanjing, or in English it's called the Mathematical Classic of the Zhu Nomen. So the first part of that text is written as a dialogue between a historical figure from the 11th century, the 11th century before the Common Era, so this is very ancient time ago, and a person who's described as a skilled mathematician. So the text is written as a dialogue between the two. And this conversation includes a description of what we think of now as the Gougu Theorem. So it's like the first known appearance of that theorem in ancient China. The statement of the theorem in both cultures is equivalent. It's the same knowledge, but the proof of the theorem in both cultures is different, which is kind of interesting. So in Euclid's Elements, the proof involves something that's known in mathematics as the windmill diagram. And the proof in the Chinese context is a method sometimes called the piling up of rectangles. So the demonstration of the theorem is different, but the theorem itself is the same.
It is evident that even historically, mathematics was a foundation to everyday life. Different tools were created to simplify tasks or to determine key information like what time of day it is. In our next example, we learn about an instrument that was used widely across the world.
The astrolabe is basically an ancient astronomical device. It's one of the first mechanical instruments for observing the heavens. It's described in some texts in Greek antiquity, and it's thought to be the instrument that the ancient Greek astronomer Ptolemy used to record a whole bunch of values that were passed around through the Middle Ages. It's kind of perfected in about the 11th century under Islamic rule, mostly as a way of reckoning time. At its most basic function, what you do with an astrolabe is you hold it up, you point the little movable stick in the center to a star that you're interested in, and you read off the values that it points out. That will tell you local time. In about the 12th century, an Arab astronomer listed about 1,000 different algorithms that could be run on the astrolabe to calculate when you should fast, when you should cut your hair. Remember, in the Middle Ages, the texture of time was set by ritual. So these devices were a way of working out your relationship with the divine. Now, the astrolabe by about the 14th century has spread as far as England and India. In India, there's a caste system at the top of which are the priestly castes who deal with abstract things like mathematics. And at the bottom, there are the kind of artisanal castes who deal with things like the engraving. Now, engraving graduations on an astrolabe is an incredibly difficult technical problem. If you're off by, a thousandth of an inch, suddenly you don't know the time, right? So now, and even in the case of Europe, precision graduation is not something solved until the steam age, the 1750s. Everybody just kind of substitutes numbers when it comes to figuring out an astrolabe for a new latitude. They make these for specific places. So if you were in Delhi, you'd buy one for Delhi, but if you were going to Baghdad, you need to buy a Baghdad one, right? Now, to redo the calculations for Baghdad, you just substitute a few numbers. But to redraw the entire map of the astrolabe is a much more difficult technical affair. So you see that the kind of intellectual labor involved has more to do with the hand than the head in a way. And I think that, that's an interesting way to view the history of mathematics, as what are the social classes that develop around that distinction between the head and the hand? There's many reasons why the history of mathematics is more complex than we might realize. Maths didn't begin with the Greeks. It's much older and much less bounded than we think of it as. I think in my own work, something I've seen, especially when we consider the issue of colonialism, is the fact that, maths isn't something that's static, especially over the past 100, 200 years. It's developed at quite a rapid pace. The first British writings on mathematics in India come almost 200 years after the British landed in India. So the first trading factory set up in about 1600, and the first writings on mathematics are in like the 1780s. And mostly people are responding to French reports that had reached England by that point, that in South India, there were a class of astronomers that could calculate the time of an eclipse, a solar eclipse, in their head. Now, in Europe at this time, this was something that took literally days because of the number of calculations that were involved. So, these rumors that in India there were a class of priest astronomers capable of mental feats is something that the British, the French, and then the British tried to explain. In the 20 years between about 1780 and 1800 in India, a ton of things happened. During that period, most of the major powers in North India, especially like the Mughal Empire, the Marathas, and what's now Maharashtra, Bombay, they're slowly beaten back into capital cities. And by about 1800, 1810, Britain has hegemony over the subcontinent, which means that, they're the paramount military power. Circa 1780 or so, the British are much more cautious. They are aware of what they don't know. After about 1810, they don't need to know what they don't know in some sense. There's nothing thought to be gained from the knowledge of a conquered people. So rather than trying to adapt mathematical methods into, say, British practice, what you see is a writing of Indian mathematics into history. This is a developmental stage in the history of mathematics. Rather than a set of techniques a present-day people uses, this is something that is ancient but has been preserved. So there's a kind of very subtle shift from like, this is maths in the here and now, to this is just a vestige. This is something that's remained and that these people can still do. And that's why in 1760, the French were meeting these people who could calculate eclipses in their head. In some sense, this is the history of mathematics in India. It's the history of a conquered people whose techniques were worthy, but would have led nowhere, and so it assimilated into the history of mathematics and came to represent a stage, but not an independent tradition. An analogy I would give is with the story the victor tells after a fight. You don't want to minimize your opponent, because then in some sense the prestige you gain from having defeated them is lesser. You want to tell the story of the vanquished in such a way that makes you seem like the natural victor, but also that you've conquered something worth conquering.
In learning about this history, we see that mathematics, like all other knowledge, was part of everyone's life worldwide. So in talking about Black, Indigenous, and people of color within STEM, it's also important to recognize women in STEM.
Since I've been teaching history of mathematics, it's been one of my goals to learn more about global history of mathematics and to represent the contributions of many different cultures and societies. Even today, when we're talking about women in STEM or talking about narratives around women, you hear it mentioned many times, this is the first time a woman did this, or first time a woman of color did that, or whatever. And when you actually look at the history, it's often not true. There is actually a long history of women making contributions in all kinds of fields. It's just that we don't always remember that history, so we have to keep becoming the first in every generation. And one of those women is Miriam Mirzakhani, who's originally from Tehran, who won the Fields Medal in 2014. She's now very much an inspiration to women from all countries. There's a couple of well-known mathematicians from the States we can think of. Euphemia Lofton-Haynes was the first woman of color in the United States to obtain a PhD. The book Hidden Figures, which came out a few years ago and was turned into a movie, highlighted the contributions of women of color at NASA who survived a lot of institutionalized racism. And despite all of that, they made fundamental contributions to putting a man into orbit around the Earth. Those stories are there. It requires us to reevaluate what stories we tell and why we consider those to be important and how they serve the future, because really the past is only useful to us in terms of what we need to know today and where we want to go.
Looking at the history of maths reminds us that maths isn't a series of revealed truths. If you sit there and you pull apart these words like mathematics or sources, you see that the narrative just becomes more inclusive, because suddenly, you realize that the methods of stellar navigation used by like First Nations people are just as complex as early representations of geometry in the Greek corpus. And these kinds of things are almost unescapable when you look at the record.
So to wrap up this episode, I asked Sylvia and Prashanth if they were adding to a science textbook, or in this case a mathematics textbook, what would be on their missing page.
If I were to pick a set of missing pages to appear in a history of mathematics, it wouldn't really be mathematics. It wouldn't be sources. It would be something that contextualizes how we know what we know. It would be, say, a description of the only known fragment of Euclid's Elements, which is a school kid's rough jottings with a hasty little diagram drawn in the bottom right corner. It would be a page that just explains where this thing was found, that it's never been carbon dated, and that it's just a piece of a school book carried forward.
We've really been thinking a lot in all disciplines how we can respond better to racial justice and equity. So on my missing page in History of Mathematics would be contributions from the works of African-descended mathematicians around the world to have greater representation for that group who have often been left out and made invisible. And so it would help promote equity and inclusion, because it's true for all of us that when we see ourselves represented somewhere, we feel like we have ownership in that subject and in the discipline.
Thanks for watching The Missing Pages. We hope this gives you a more accurate picture of the history of science and the peoples who continue to play a part in shaping our view of the world today. Be sure to subscribe to our channel for more content and follow SciExchange on social media.